So hello guys. First of all, thank you for attending yesterday's session and for coming to day two of the workshop on system design by the GNU Linux users group. Uh, so before that, we would like to say that yesterday there was a minor technical glitch at the end of the workshop because of which you couldn't really know what the entirety was. However, we completed everything till cap theorem. Okay. So just giving you a quick revision of that, cap theorem says that if you have a particular partitioning problem in a system, then you can guarantee either one of consistency or availability. So out of these three things, that is C for consistency, A for availability, and P for partitioning problem, just two out of these three can coexist at any point of time. In case you haven't watched yesterday's session, you could go and watch yesterday's session because that covers all the basics of system design. So today we'll be covering one or two basic concepts, after which we'll delve straight into solving an actual system design problem at the high level, obviously. So the first concept that we have today over here is microservice architecture. So what is microservice architecture? Whatever we have been seeing mostly till now, whatever development you have done in college, it is mostly monolithic architecture. That is, you have a client, you have a server, you're interacting with the server, you are having all the various API calls in a singular server, you are trying to manage everything from one point itself. However, in today's changing scenarios, today's business needs are so high. The number of users on the internet are increasing exponentially day by day. The demands of the people are increasing day by day. Especially in this COVID times, the amount of technical access which people have has gone exponentially high in terms of people using different services for work, for personal use, etc. etc. So basically, in a nutshell, we can safely say that the demand for services on the web has grown exponentially, and monolithic models are no longer being able to handle such scalability factors. So over here comes the concept of microservice architecture. So let's just look into it. Microservice architecture is basically a collection of distinct, loosely coupled, independently deployable entities to make a system work. It's a modern solution to cater to increasing business demands. So if you can see the particular diagram over here, you will see that the client is interacting with an API gateway. Okay. So what's an API gateway? What's an API? Basically, an API is application programming interface. It's basically a medium by which you can actually interact with your backend in simple terms. Okay. So if you have an API gateway, this API gateway connects you to various microservices instead of just connecting you to one server in order to fulfill your request. Now you might find it a little difficult to follow, so let's just go and understand it at a very basic level. Okay. So let's say you are running a pizza store. Okay. You want to make it a franchisee model. You want your pizza store or whatever, your burger joint or whatever, to become like a McDonald's or a Burger King, and you want it all over the country. So initially, let's say you start with one particular shop. Okay, so you start with one particular shop, shop one. It has all the seating arrangements. It has certain chefs over there. People are preparing different things. So there are many things over here which are making your the store run. So currently, let's say you have two chefs, and you have various things on your items. You have your burgers, you have your, you have your burgers, you have your fries, you have your burgers, you have your fries, and similarly, you're going on adding to your menu as and when you deem fit. Now, let's say your joint has, somehow reached a level where you can think about scaling it further. So what you do is you keep adding chefs. Let's say now you took your total count to 5 chefs, right? Now you are introducing the concept of speciality. So the concept of speciality says that, let's say there are 5 chefs which you hired. Out of that, 3 chefs are very good with, let's say, non-vegetarian dishes. So they are very good with non-vegetarian dishes, and there are 2 chefs which are very good with vegetarian dishes. Okay. So veg dishes. So there are two chefs which are very good, three chefs which are very good with non-vegetarian dishes, two chefs which are very good with vegetarian dishes. Similarly, there could be other classifications like certain certain chefs are experts with Italian, or certain chefs are very good with, let's say, Indian food, or something like that, right? So in order to make your thing function better, what you could do is you could create microservices. So instead of viewing your entire system as five chefs, you could create two microservices of three chefs and two chefs each. Now, whenever you have a non-vegetarian order, you know which microservice to contact. If you have a vegetarian order, you know which microservice to contact. In case you have a mixed order, you could have an intermediary microservice which will keep track of all the orders. And it is responsible for combining all the orders which come from the different microservices and then sending it out to the customer. So basically, you could have something like you have a customer, right? Then you have a microservice here. This microservice is responsible for order distribution. And then you have a veg microservice and a non veg microservice. So what does this do? How does it help? First of all, it optimizes the performance of your, the restaurant, whichever you're owning. Why? Because the chefs which are specialized in veg orders, they know that they will be getting veg orders only. So they will make tastier orders. They will make faster orders. Similar thing goes for the non-vegetarians, right? Now let's say you have further expanded and you have two joints. Okay, so this is your joint one. This is your joint two. Let's say store two. Inside store 2, again, you have similar microservices of the chefs. Now, what you do is, now that you have scaled to a great limit, you see that you're constantly facing the problems of breads, okay? Because breads are something which will be used, or let's say every ingredient, because since it's a hotel chain, you must know that all hotel chains follow the same recipe, right? So all the materials, all the breads, whichever they use, it's the same. So you create another microservice, let's say somewhere in the center, okay? Your, or which is not accessible to the users, obviously. It's your own microservice for your own needs, which keeps track of all the bread production, of all the other ingredients production. Now this microservice is responsible for ensuring proper supply of breads and other ingredients to store 1 and store 2. So whenever store 1 and store 2 run short of a particular ingredient, or they need a certain amount of ingredient, they know which microservice to contact. So this is how a concept of microservices works when it comes to a restaurant chain. That is, you try to keep specialized people together without any conflicting opinions, right? The vegetarian chefs don't need to know what the non-vegetarian chefs are doing. Similarly, now let's just look at it very briefly in a technical scenario. Okay, like very briefly in a technical scenario. So let's say you're developing a system. Now, when you are developing a system, there are many things which need to be taken care of, right? So let's say you are working on a social media platform. Let's say, so you're working on a social media platform. So there are many features, right? So social media. So there are many features. I'll better type it so that I handwriting is a little more legible. So let's say there are things about posting posts. Then there is another requirement for a timeline. Then there is a messaging service. Then there is a likes and comments service, etc, etc, right? So there are many services which are provided inside a single social media platform. Now just imagine the number of developers that will be required to work on it. So just assume one thing: will it be better if I cram all the code of all these services into one single architecture and just host it somewhere? Will it be easy for me to get such a huge developer team who all know how to work on a same language to keep working on all these things together? Do all these things are all these things equally compatible with each other? The answer is a big no. So whenever you are developing large scale applications, it's better to develop each feature or each functionality as a microservice. So if I create a microservice in the form of a messaging service, so the messaging service is a separate microservice. Now it is the responsibility of the developers of the messaging service to develop it as and when they want, as and how they want, in fact. So let's say they are good with a particular language, let's say JavaScript. So they will do it via JavaScript. The people responsible for the timeline are, let's say, good with C sharp. They will do it via C sharp. However, they will just give proper API endpoints to the others. So the people who are developing the messaging service as a microservice will create a proper endpoint, an API endpoint for others to use. And in such a way, there will be a huge application called a startup application, which combines all the microservices together. So they will just, it will just give API requests to different API endpoints, and your whole application comes together. So basically, the entire idea is, instead of cramming everything in one place, you make independent microservices. So this messaging service will be a microservice. Now imagine this social media has another branched off social media, right? So let's say, okay, like you could go with Facebook and Instagram, right? Like how connected they are. Your Instagram messages, you can see them via Facebook, etc., etc. Why? Because that messaging service is a microservice. You could visualize it that way. So if your messaging service is a microservice, you can use the same microservice, same code for multiple applications without actually having to rewrite that code in another application you make. You could also sell your microservices. So for example, you're the owner of a company which has a messaging microservice. Now another company which needs to integrate messaging into its app can pay money to you, and you can actually provide your own messaging microservice to them. All they need to do is have the API endpoints and just send their API requests to your messaging service, and their work is done. So microservice architecture is the need of the hour. You can scale each architecture separately at your own will, at your own pace, at your own cost. You can develop it in any language of your choice without actually depending on the other components of your system. So this is what is microservice architecture. It's something which is very important and something which is really, really picking up pace in recent times. So yeah, this was about microservice architecture and how it is different. Okay, so now let's delve into an actual system design problem. So the problem that we are talking about here is a very popular problem. It's an easy problem, but a good problem to start with. Okay. So the problem is designing a URL shortening service like tinyurl, bitly, bitdo, etc., etc., etc. So along with these problems, I'll be sharing some tips which you should follow during system design interviews. Basic tips, basic interviews. So we'll be solving this real life problem, and then accordingly, along with that, we'll pick up some concepts on the way. So yes, this is what your interview tells you: designing a URL shortening service like tinyurl, bitly, etc. Now your interviewer might choose to give you what it does, or you could just ask, so sir or ma'am, overall, what does this do? So the URL shortening is used to create shorter aliases for long URLs. We call these shorten aliases short links. Users are redirected to the original URL when they hit these short links. Short links save a lot of space when displayed, printed, messaged, or tweeted. Additionally, users are less likely to mistype shorter URLs. As simple as that. You could take an example. This huge link of your stream could become bit.do slash something 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 of just 5 or 6 characters, right? So this is what your interviewer gave you. He could just give you the question, design a URL shortening service. You have to clarify that, so this is what you mean, right? And this is the purpose which it will be used for. Otherwise, in some interviews, the interviewer might give you that too. So just be prepared for either way. Fine. So as soon as you hear this, what do you do? There are some people who start jumping straight onto answers. No. First, be very clear as to what the interviewer wants from you. What is the exact product that he's demanding? So the next step is to ask questions. What does the service do? What are the main features, functional requirements, optional requirements, and flow of the application? Also ask him, what is the target market? What kind of reach are we expecting? Number of reads and writes per second, the estimated storage that we would require. So these are certain questions which you have to ask your interviewer line by line. Okay, just don't throw everything at him or her together. Basically, start building as to what you need to know. So first, okay, let's go to what are the requirements functionally. What should be provided to the users? So functional requirements. Given a URL, our service should generate a shorter and unique alias of it. This is called a short link. The link should be short enough to be easily copied and pasted into applications. When users access a short link, our service should redirect them to the original link. Very simple. The interviewer in this case has removed all complications, no private links, no time expiration and things like that, since it's a basic course which we are delving into. So yeah, this is what we require for now. A simple link which creates a short URL and which gives redirects me to the original link as soon as I put the short URL in the browser. Okay, so these are my functional requirements. After that, there is something called non-functional requirements. So after hearing the functional requirements, it is your responsibility as an interviewee to come up with non-functional requirements. So what could the non-functional requirements for this be? First, the system should be highly available. Why is this required? Because if our service is down, all the URL redirections will start failing. Okay. URL redirection should happen with minimum latency, and the shorted links should not be predictable. Okay, so that's a very basic thing. So obviously your interviewer will help you with these, but you should try to come up with them first. So after getting the list of functional requirements, you should throw these at the user, at the interviewer, I'm so sorry, at the interviewer, that okay, sir, ma'am, I think that since these are the features, so I just want to note down the non-functional requirements for this. I think it should be highly available, because if the URL itself is not available, the point of having a service does not, like, it's pointless. And it should happen with low latency, and nothing should be predictable. Perfect. So, okay, fine, good job. So after that, we come to the traffic. Now the interviewer will only give you some information. So one information is read is to write is 100 is to 1. Now this is something which even you can predict. So you could, if this interviewer asks you that what is your estimation, you could say that yes, for every link generated, I am hoping, let's say, on an average 100 people will click it. Now obviously this could go up, this could go down, it's all an assumption, but over here we have estimated 100 is to 1. Number of new URLs generated per month, 500 million. So this is something which your interviewer will give you in some form of the other. He could either give you the number of new URLs generated, he could give you the number of unique users, it could be anything. But one basic figure he could give you. So here we have considered 500 million per month. And after that we have derived certain calculations. Number of reads per month, since the number of writes per month is 500 million, the number of reads will be 100 into 500 million, which is 50 billion. Writes per second is 200 and reads per second is 20,000. So these are certain basic calculations which we have done. Storage requirement, we have assumed 5 years. Again, you can ask this from the user, that how many years do you want to store something in. So let's say if you introduce a feature of link expiration, obviously a YouTube video with a shortened link 5 years back, you don't need to store it for another after 5 years, right? So over here we have assumed for 5 years. So again, we have estimated that for one URL we would require roughly 500 bytes, half a KB. So accordingly we have estimated the total space that we will require, that is 15 TB. Also we have calculated our cache requirement. So over here we are following the 80-20 rule. The 80-20 rule says that in a day, whatever requests I am getting, okay, whatever requests I am getting, 20% of the hottest requests I'll store it. You could obviously keep it 30%, 70%, 50-50, but then that would monumentally increase the amount of money you are investing in your cache. So we have considered 20-80 over here. You can make this assumption, you can ask your interviewer, whatever. So we are assuming that yes, 20% of the daily requests we are doing it. So we know that we are getting 20,000 requests per minute, per second, right? So we just converted to 3600, which is 1 minute. So which is 1 hour to 24 hours. We are requiring 500 bytes for that, and just 20% of that. So we'll be requiring 170 gigabytes of cache. So 170 GB of cache is something which fulfills our requirements. So these are some basic calculations. In your college level interviews, you might not even need any of these, as the interviewer will just ask you to go at a very, very high level superficial implementation. But since we wanted to like just give you an idea that something like this could happen, we have done all this for you. So yeah, so these were some basic system metrics that we delved into. Now let's start with designing our system. So the very first thing that we need to think is my API. So what exactly are the calls which will be made from the client to the server? What exactly do I need from the server? It's simple, right? First is I am a user. I logged into my website, whichever website I am creating, tiny URL, bit.do, bitly, whatever. and I need to generate a short URL, right? So I put a long URL inside the box. I click on generate, and it should give me a short URL, right? So create URL, user key, just to ensure that I'm logged in. So I'll have a unique key, comma original URL, and it returns a string which is a short URL. As simple as that. And another thing is, when I'm using a short URL, so let's say I am in the browser, I type bit.do slash, let's say jp67wq. So this will trigger a request of a get URL, which will return the original URL and redirect me there. So these are the two basic API calls which we will be using in this application. So step one, whenever you get a system design question, ask what the application does, get functional requirements, get the flow of the application, try to craft out your own non-functional requirements. What are the system requirements that you would like to be a part of the system? Make sure that you have all the bases covered. See if your interviewer wants to give you some data as to what your target market is and what exactly is the volume of data you are dealing with. And then we move to two things, that is creating the API, what kind of requests will go, and creating the database schema. So these two steps are interchangeable. You could actually do database schema first and then API next. But since in this application the API was pretty simple, we did that first. So yeah, you could go with database schema first as well. So there are two things which I am storing: URLs, where the short URL is your primary key, uh, because every short URL is unique. It corresponds to a particular long URL, and a user ID, the user who created it. And then we have users, who has a user ID, which is the primary key, the password in certain encoded form, and other info, whatever you would like to store about the user: address, phone number, email ID, things like that. Fine. Okay. So now what type of database should be preferred? So now we haven't really covered everything in big detail, but I'll just give you a small perspective into SQL versus no SQL databases. So for the purpose of this, it would be better if we have a NoSQL database. And why exactly, we'll just cover it right now before moving further into this question. So like, just let's have a look into that. Yeah, so talking about SQL versus NoSQL databases, I'll just give you a very brief structure. So when we are talking about SQL databases or relational SQL type databases or relational databases, we are talking about databases with a rows and column structure. So the typical columns you have which denote the various fields, and then you have various rows populating those fields. That's the SQL type databases or the relational databases. Now these databases are the oldest and one of the most trusted forms of storing data, and they are ACID compliant. That is, they follow the properties of atomicity, consistency, isolation, and durability. So as these words suggest, the transactions which are made on these databases are ACID compliant. That is, they are completely reliable and you can use them for complex data calculations. What is their downside? Number one, when you are a part of an SQL database and you have defined your columns and your rows, right? So your columns basically. Now let's say halfway through your system, all of a sudden you feel the need for adding another column. That means restructuring your entire database. So SQL type databases, although they are very sturdy, they are very reliable, they allow us to do a lot of complex data manipulations. Example, joins, natural joins, and many other SQL queries can be used to achieve a lot of data manipulation. They are very sturdy. Their downside is, first, they are hard to scale. So it's just vertically scalable. Horizontal scaling will lead to a lot of problems which arise. We have discussed some cons while discussing database partitioning as well. And also, in case halfway through the system you need to make a change, then you need to make a change in the entire database. So either you put null values in the initial entries of the database, or you have to restructure the entire database. So SQL databases give you power over your data, yeah, like a lot of data manipulation power, number one. Number two, it gives you ordered data, well ordered data. And the cons are, obviously, it's less flexible to changes and it's not very scalable. Now we move to examples, obviously MySQL, SQLite, PostgreSQL, etc., etc. Now we move to NoSQL type databases. So the NoSQL type databases are basically anything which are not rows and column structure. So they could be key value pairs, just like you have a JSON format or something like that, like something similar to a JSON format, where you have a key, let's say name, Mohit, you know, college, NIT Durgapur, club, GNU Linux users group. And then you can have the very next entry, which is completely different from mine. So it could be like name, let's say Sumit. Then instead of college, it's written school. Instead of club, it's written society. So basically, no SQL type databases allow us to store data in forms which are not rows and columns. They do not have a rigid structure. They are very, very flexible, and they are easily scalable horizontally. Why? Because they do not have a rigid structure to them. So you can easily scale them across multiple data structure, multiple servers, across multiple entities. Obviously, they are not ACID compliant. There are certain compromises which are there. However, they are best for systems where scalability is the main focus and we are not handling complex data. Examples include MongoDB, Cassandra, etc., etc. So now, having known this brief introduction of SQL and NoSQL, we can very well say that in our system, which is a tiny URL generator, we know that we are not having to do any data manipulation. We just need a scalable system which can store simple data. So this is the reason why we would prefer to go with a NoSQL database in this regard. It will also help us to change the structure of our application a bit. For example, if you want to add functionalities like the data will expire after a certain amount of time, so you can add certain fields like creation time, deletion time, according to your preference. So this is why for this particular application, a NoSQL database takes the cut. Okay, so now let's talk about one of the prime things which concern our particular application as to how will we generate the short URL. So, okay, you see a question where you have a long string and you have to generate a short string. And then there is some form of mapping which is there between the short string and the long string, right? So the very first and common and genuine answer which can come to your mind is encoding. So you use some algorithm, you find out the hash of the particular long URL which I've put it there. It could be MD5 or it could be SHA-256 or any other encoding hashing algorithm. We are not that's not the ambit of this discussion. So we create a hash of that and then we find out a encoding scheme, maybe base 64, and then we create a shorter URL and return it, right? So this is something which is very logical and you should in fact propose this as something to your interviewer. Now your interviewer tells you, okay, fine, good. However, do you think there are any problems with this particular approach? So let's just try to delve into that a bit as to what could be the problems with this particular approach. So let's say I have a site, right? I am user one and I try to generate a URL for abcd.con. Okay, so it will encode and then it will return to me a URL like this. Let's say my service name is bit.do itself, bit.do slash. Now this part is, let's say, A16HJK. Okay, something like this. Now this is one URL which I want to circulate for this website, right? abcd.com. Now another user, user 2, yeah, another user, user 2, tries to do the same. He will get the same thing back in return. So he will get the same thing back in return. That is bit.do A16HJK, which is totally incorrect. Why is it incorrect? Because when I am dealing with such systems, I need every user created link to be unique. For example, when you go to a site like bit.ly or bit.do or tiny URL, and when you put in a URL over there to shorten, do they tell you that this URL has already been shortened? No, right? Every user should have the right to, as many times as possible, create unique shortened URLs for the same URL, unique to that user. Then they can add analytics to it as well. Then they can monitor their website in different ways, etc., etc., etc. It could also be useful for mechanisms such as referral mechanisms, as to who has clicked whose link more. So basically I need different URLs created by different users, right? So in an encoding scheme, if I do this, In that case, I will get the same URL back, which is something which defeats the purpose of my application. So this is problem number one. Now let's see what problem number two could be. So the problem number two could be something called URL encoding, right? So now let's say I have abcd.com slash whatever. Let's say I have um, index question mark id equal to 5, something like this, okay? And over here I have something like slash index. So let's say, yeah, id 5. So basically, hypothetically, just assume that both of these redirect to the same URL, right? However, because I am using an encoding scheme, so therefore both of them will return the same result, will return different results, although they are essentially pointing to the same URL. So basically, whenever URLs are, URL encoded in this way, these encoding mechanisms tend to fail. Encryption mechanism tend to fail. Therefore, we have another way out for this. Something which makes this functioning much simpler. So the method that we finally should look up to is using an independent key generation system. Okay. So let's just see how that will work. We'll work out all the pros and cons of the same as well. And let's just see how exactly will we working around with them. Okay. So first of all, how can we generate the keys, right? So let's just work with a base 64 encoding scheme, base 64 encoding scheme where the KGS or our key generation service will keep generating new keys on its own independently, irrespective of the long URL. There need not be a relation between the long URL and the short URL, right? So we independently keep generating the keys, which are base 64 encoded, and then we keep returning those to the long URLs or to the users, right? So first, let's just go down to step by step. So first, let's use the base 64 encoding scheme. So what exactly is the base 64 encoding scheme? The base 64 encoding scheme says that, okay, yeah. So basically just like base 10, everything, every letter will have up to a base of 64. So let's say if we had a 6 digit number, right? Then in a base 10 system, how many different combinations would have been there? 10 to the power 6, right? 10 to the power 6. Similarly, if we have a 6 alphanumeric character with base 64, right? We'll be having 64 to the power 6, 64 to the power 6, which is equal to approximately over 60 billion, okay? Which is over 60 billion unique keys. Now, considering the system that we have at hand, considering the fact that in 1 month we are getting approximately just 500, million requests, so 60 billion unique keys for now is serving our purpose well enough. Okay, so for now we are going by 60 alphanumeric characters, 60 billion unique keys, more than 60 billion unique keys, right? So we go with this. So what we are doing is my key generation system is basically trying to generate all the unique keys that are possible in a base 64 alphanumeric system. Okay, so it will generate more than 60 billion unique keys. Obviously, now we are worried about its database size. So its database size, again, if you consider that every, yeah, if you consider that every character is taking 1 byte, and then we have over 60 billion 60 billion data over there, and there are 6 data associated with it, so we could assume that it's somewhere again along the line of 450 GB. Okay, so basically I have a key generation service. This key generation service will have a separate database called the key DB, you could say, okay, whose storage capacity is approximately 450 GBs. it will store all the unique keys that have been generated by the key generation service. Okay, these unique keys will now be assigned to the long URLs, which we will receive one by one, like as and when they come. So as and when they come, we will keep generating these new URLs. Cool. So this is how it works. Now let us just try and answer a few questions or some loopholes which could be there. Okay. So let's say, yeah. So let's say we have like, two, three servers, application servers, and this is my KGS, the key generation service, which is running some kind of algorithm. This is my key DB. Okay. This is my key DB. So they are constantly, concurrently asking this to give them new keys, new keys, new keys, new keys. Constantly they are asking for new keys. We had seen the number of writes per second is 20 per second, right? So we are concurrently getting multiple requests to our KGS to give it new keys. So what the KGS can do in order to ensure that keys which have been used are not used again is it can, have two separate data. It can have another separate data for used keys, so it can have like, divided it into two, used and unused. Okay, unused. So whenever my key generation service gives a particular key to a server, right, it puts it in used. Okay, so it moves from unused to used. So this ensures that one particular key is not given to more than one server at a time. Now in order to speed up the process, what can be done is, let's say at a fixed interval of time, okay, let's say at the beginning of the day, what the KGS does, it's in its RAM, okay, in its RAM. So this is the database. In its RAM, it can store a certain number of keys and it can put all those keys under used. So let's say it took 500 keys, okay, 500 short URLs, and it put all of them in used. Worst case, by the end of the day, let's say we are flushing it every one day. Worst case, at the end of the day, some amount of keys will remain unused, which will be wasted. But given the leverage we have, over 60 billion unique keys, we can afford this loss because this will speed up the process. This will prevent us from, making a transaction from a used database to a unused database to the used database every time. So it can just load all that data to a memory and directly, shift all that data to the used database from the unused database. This is one. And secondly, in order to ensure that more than two servers do not hit on the same data, we have to have in some kind of a lock-in mechanism. Lock-in mechanism. So on every data, on every key which is there, there is some sort of lock-in mechanism to ensure that more than one server does not take the same key. So with this, we can solve the concurrency problem by preloading data into memory and putting all of them inside the use section of the database. We can save a lot of time and latency. Another thing which we can do is we can create a separate cache at this level. Okay, we can create a separate cache at this level for the application servers. So we can take in some new keys, and for every application server, we can create a cache in between. So by creating a cache in between, what we are essentially doing is we are allowing the servers to query faster. We do not have to take data from a database every time. We do not have to go to the KGS or the key generation system every time, and we can directly take the data from the, the buffer or the cache. So in this way, we can heavily optimize this performance, number one. Number two, we can avoid all the loopholes which were there of an encoding system. That is, we do not care about, which user is doing it. If someone requests for a shortened URL, we give them a unique shortened URL. So that's another advantage. Third is we can actually make it pretty fast without having to calculate, because over there we were running an algorithm of calculating an encoding scheme, and over here we are just creating pre-generated values. We have already done all the calculations from before, and all we need to do is allot. And obviously by using caches, etc., we can further speed up the performance. So in totality, the key generation service completely, satisfies our purpose. Cons. The con of this is the KGS could become a single point of failure because it has a separate hardware associated with it. Okay. It has a separate cache associated with it, a separate memory associated with it. The key generation service could become a point of failure, right? Since it's an additional component which we have added to the system, it becomes a key point of failure, single point of failure. So basically, again, there is no other option for that. You keep a duplicate. Again, keeping a duplicate is worth it. And again, fights of the trade-offs which we have made in deciding over the encoding service. So yes, it could be a single point of failure. So just have another key generation service, which is a replica of the same in place. That is worth it compared to the drawbacks which encoding was providing to us. So with this, we understand how the keys are being generated. There's such a small diagram just to, like have a view. So basically the client, the application server, that's the main database which you see there. And this is the key generation service, which is dealing with the key DB. So which is dealing with the key DB, and then that is providing its data to the application server. So in this way, key generation could work in our system. You might have understood all the trade-offs associated with it. Okay, so now that we have understood how exactly are the keys being generated, stored, and supplied to a server, as well as how exactly the entire process of writing is working, let's take a look at how exactly should our database be partitioned. So there are two ways by which we can actually try to think of partitioning this database. So obviously the first one is the range-based horizontal partitioning. So it's basically the horizontal partitioning that we were talking about. That is, we're divided on the basis of rows. So we could have the starting letter or number of the short URL. So let's say since it's base 64, so we could have different variations. So based on that, we create different database shards, and then you could store the data in various shards. However, the problem with this entire thing is, again, it could lead to uneven distribution of data across various databases, along with pretty much a good amount of wastage of space as well. Also, there is another way by which this could be done, that is a hash based partitioning. So basically the short URL which you have, you can easily convert it to a hash. So let's say if we try to hash it with some form of algorithm which converts it into a number between 1 to 256. So we could have various database shards from 1 to 256, and we could distribute it amongst those. So the con of this could be that it leads to uneven distribution or certain things overflowing. However, there is a solution in hash based partitioning called consistent hashing. We won't delve into consistent hashing as it's a good concept. It's better if you read it separately after understanding everything about hashing. Since we are not covering hashing in details in this, we are not covering consistent hashing as a part of this course. However, you can easily look up YouTube videos and read articles on consistent hashing. Basically, I'll just give you gist. Consistent hashing basically helps you dynamically hash. So let's say if certain partitions of the hash are overflowing, or there are certain deletions, in that case, you can automatically rehash without having to delete your entire database. So this is one advantage with hash-based partitioning. So basically, both these things have their own set of pros and cons. So you could pitch both to your interviewer and then accordingly just go along with what the interviewer says. So, he or she could basically put in a certain list of conditions. Those conditions might tell you that, okay, a range based partitioning over here is not something we are looking for. So you go for a hash based partitioning. However, if the interviewer tells you that, okay, time over here is a prime factor, we do not want a hash based partitioning because every time then we have to check for a hash and then redirect. That could be a single point of failure. So in that case, you go for a range based partitioning where you just see the first letter and accordingly you know which server or which database is basically hosting the needed or required data. So in this way, you can work around that. So but yes, these are the two primary ways by which we are not going for horizontal, we are not going for vertical partitioning, because there's hardly anything worth partitioning for in that. It would just create problems, as you would not be able to query properly. There are not many columns which we are storing anyways, so there is no point going for any form of vertical partitioning in this case. So now, yes, now we talk about caching. So we have already calculated before that the estimated cache size needed would be approximately 170 GB. So now we can use a single machine to handle this along with replicas, obviously, because we do not want a cache to fail. Because trust me when I say this, big applications depend a lot on their cache to ensure low latency. And we know that one of the non-functional requirements of this particular application is low latency, right? So we cannot afford a cache failure. You could obviously use multiple servers for hosting your caches, which independently have different sets of data according to different things. Also, the least recently used algorithm could be used for cache replacement. Why again? Because see, when you're talking about tiny URLs, right? Just think about its usage. What is its usage? Let's say you have a fest in your college, right? You have created a form, let's say a Google form or whatever, and you want people to register. Now the form link is huge, and you want to, shorten the link or any link, let's say a website link of the fest or whatever. So you create this link, shortened link, and you circulate, right? So basically, after you circulate, you expect people to click on that in bulk, right? So basically, the entire ideology behind this service is I have something coming up. I need to put this link in my publicity posters. So I'm expecting many people to click on it in a certain period of time. So recency is a very important factor. After your fest is over, right? Will that link be valid any longer? Like it will be valid, obviously, but will it be of any use? Will many people click on it? No, right? You can afford to give those people some low latency and rather replace it with a link of a new fest which is upcoming, right? So basically, the least recently used algorithm, as the name suggests, deletes the least recently used element in the cache and replaces it with a new element. So going by why what the purpose of this application is, the least recently used algorithm could be a perfect cache replacement policy. So yeah, so now we look at this diagram. This diagram basically shows how exactly will a client access a shortened URL. So basically this is the client, okay? The client sends in a request for a shortened URL to a server. There will be multiple servers. We'll talk about the load balancing after this, which will be the last thing which we'll talk about. Okay, so to a server. Now that server will redirect it to a cache. See in the cache, if there is a cache miss, that is URL not found, or URL found, whatever. If it's a cache hit, okay, let's say URL found, it will come back to the server. If it's a cache miss, that's it's a URL not found, then the server will query the DB. Okay, they will query the DB. Now, if the URL found, then first it will update the cache that okay, so this URL might be in demand. So use the least recently used algorithm and replace this with this new data, and it will return a cache URL found to the server. And if it's a URL not found, it will send a URL not found to the server. If there is a no URL found thing, it will return an error, URL not found, it does not exist. Okay. If there is a URL found, now basically we haven't really spoken about this, but this is, you could say, an intermediary service for validation. You can skip this. It totally depends upon the requirements. We have just included it because certain times, like certain things like user has no permission, basically a final check. So we have included it. However, this is not a compulsory step. So yeah, you could directly return URL found over here, but yeah, you could just pass it through an intermediary service. And then if the intermediary service says yes, okay, good, yes, okay, the it's fine, otherwise you give an error message. So this is basically the entire structure of how the system of getting the longer URL after you put in the shorter URL works. Okay. So now with this, we move to the final step of this particular workshop, which is the load balancing. So you can see the whiteboard over here where I have a similar diagram. So where can we implement the load balancing? So the load balancing can essentially be implemented in two areas over here. So let's just demarcate that. First, obviously, the load balancer has to be there between the client and the application server. So obviously there will be multiple servers. This one server won't suffice. So the load balancing will help in redirecting it to multiple servers. Obviously, right now the best way to help like divide your data into servers could be the round robin method. Okay, since nothing much is specified, You could just go with the round robin method, considering equivalent servers for the purpose of this. Another place where you could have the load balancing thing in check is obviously between the application servers and the database. So this is another place where you could have your load balancers in check. If you're having multiple copies of your database, you want to increase the number of concurrent requests which you want to make to your particular database, you can obviously have a load balancer over there. Okay. Obviously, to complete this diagram, to make the entire system, we obviously have the KGS, the KGS with its own set of cache over here. Okay. So this cache is updated by the KGS, and we have the key DB. We have the key DB. So whenever there is a, whenever there is a request for generate, whenever there is a generate thing, obviously it goes to the KGS cache. And once it goes to the KGS cache, it updates it in the DP, it updates it in the database, gets a confirmation, and then sends the confirmation back to the user. So this is how the system of a tiny URL generator can work. Again, this is a high level design. Getting this basic understanding will help you with system design problems. There are many more harder problems. There are many more concepts. There are many more things which you need to keep in mind. But these are the basics, especially for college students who are sitting either for their first interviews, in their intern interviews, or for their full-time interviews. Having basic knowledges, having an overview of how things work is more than enough. More depth is expected from people who have a certain level of experience and have worked in companies which design large applications, and when they go for further job changes is when further system design knowledge, proper thorough understanding is expected. However, by through this workshop, we hope that we could give you a basic idea, a large overview of how things work, and how a tiny URL system could actually work in real life. So with this, we come to the end of this workshop. If you have any doubts, you can always leave it in the comment section. NIT Durgapur students can ping us on our WhatsApp groups and our Discord channel. Outside students can again leave their comments on YouTube. You can ping us on our Facebook page, on our Instagram page, wherever you want to connect with us. Please do like our video, subscribe to our channel, and please encourage us to make more content, as we want to keep serving the open source community, the technical community, the student community, in creating good content which actually benefits you guys. So with this, again, thank you so much for attending this workshop. It was great that so many people have attended it and are learning something from it. Again, finally, we are living in very tough times. Hope that all of you stay safe. Our prayers are there with all of you. Stay strong, stay safe, and may the source be with you. Thank you so much.